pleasure to have all of you here. It's nice to see all of you here. What is principal component analysis? What is factor analysis? So we have a very large data set, and very large. These days, if you look at data, data has become a big thing. Artificial intelligence is now the new electricity in town. Okay? And you would also notice that now data is becoming like the new oil. So there's something, big data analytics. I was working with someone who is working on European data, and we had 12 million data sets. Can you imagine that? 12 million. So data sets can be very large in real life. For example, do you know how much data Netflix is churning every day, every single day? Now, when you're watching one Netflix movie, do you see the data size? Okay, about 6 gigabytes of one Netflix movie, quality 4K video. Okay. So data is really, really, really increasing. And sometimes, you see, life is multidimensional. For example, as you are walking, you see people multidimensionally. But when you are drawing, you draw it on a Cartesian plane, XY graph, XY graph. But life is not XY graph. Life is 3D, not 3D, 5D, not 5D, 16D, cuboid. That's how life is. And so you need to be able to break things down, you know, investigate the number of factors underlying a large data set, bring it down. And you can compute factor scores to be able to make sure which one is influencing the work. Now, principal component analysis and factor analysis are very useful. Why? Because sometimes before you do logistic regression, you need that. Now, you guys have done multiple regression. Multiple regression is where the dependent variable is numeric, number. Okay. Now, logistic regression is when the dependent variable is binary, 0 or 1. Who can give me another example, okay, of models that are limited dependent variable, not only logistic regression. There are other variables, other models, you know, that deal with 0 or 1, 0 or 1, 0 or 1, binary. For example, you want to predict the probability of default, whether a customer will default the loan or will not default the loan. What factors will determine whether the customer will default the loan or will not default the loan? That is a logistic regression you can use. You want to predict gold price. Gold price is numeric. So that one, you cannot use logistic regression. You have to use dummy variable regression. Limited dependent. You have to use simple or multiple regression to be able to do that. So you have the gold price being influenced by the exchange rate, by the interest rate, by the inflation rate, by the GDP. That is what you have done already. But logistic is where, for example, you want to predict the probability of churning, a customer churning, a customer canceling his subscription for DSTV. Okay. Or you have a customer who is in MTN. What is the likelihood that a customer will switch away from MTN to Vodafone or to Telecel? I think that's the name now. In such a case, you cannot use regression or multiple regression. You can't do that. You have to use logistic regression. Sometimes you got to use a logit model. Sometimes you got to use toll-based regression. Sometimes you have to use censored regression. Sometimes you got to use, you know, truncated regression. And all of them, it has to do with some things related to either the thing is binary, or the thing is between 0 and 1, or the thing is truncated at some point, you know, and things like that. So please, all the things you guys are learning is not everything, you know. Just know that there are other things. And when what if the dependent variable is many? You see, multiple regression is when the dependent variable is 1. Logistic regression is when the dependent variable is 2. What if the dependent variables are 5? What kind of work you can, what method can you use? Who can tell me? Who can tell me? Raise your hand. Tell me, what approach can you use to handle situations where the explained are many? They are not just, you know, like the way the independent variables can be many. This time you can have the dependent variables to be many. What method can do that? Let me call the strong people. Those that I mentioned their names and they were smiling. can mention your name. I don't mention your name. Ukata udumo phone now, -100. Caroline, stop listening to outsiders and focus here. Pay attention. You are 10 whoever is talking to you outsider. Okay? You are not. Okay. What's the name? Albert Senator. What method can you use to do that? If it is not multiple regression, but the dependent variable is many, what will you use? Albert, are you there? I can't hear you. I can't hear you, Albert.
Can you hear me, Doc?
Loud and clear. So what method will you use?
Can I get a question again, Doc? Because I think I moved away to pick something.
No problem.
Yeah.
I'll repeat it for you. I'm saying that in multiple regression, the dependent variable is 1.
Yes.
Okay. When the dependent variable is 2, the likelihood is that you will use some of the limited dependent variable regressions, like logistic, especially binary. What if it is having multiple dependent variables? What method? Sorry?
Exploratory factor analysis.
No, my good friend, no. You should have lunch before coming. Foster, what is it? What method is that? Foster, sorry, unmute yourself. Stop picking the answer. Foster, look at me and stop looking at somebody. Yeah.
Doc, I was having issues with my network. I think machine learning.
But if you're having issues with your network, why are you getting the answer from your other side? And you keep talking machine learning, you're picking it.
No, I'm not getting the answer. I'm only alone, but my Wi-Fi is disturbing. So I'm trying to see if there is the connection because it's connected to.
And you can see it there by turning the left and see with your eye that the Wi-Fi is the problem.
No. I'm trying to check the circuits if maybe it has disconnected. Because it's
okay. It's not machine learning. Who has an idea? It starts with S. S.
Structural equation modeling.
That's it. It's one of them that you can use for that purpose. Okay. I normally teach that, but looking at time, hopefully I'll be able to do, because it's just a next level after PCA and FA. So depending on time, we'll crack that. So that is it. And that is why you need PCA, because one thing about principal component analysis or factor analysis is that it can help you identify the collinearity before you undertake a regression. Then you use composite measures. From a lot of the variables, you can combine them. Why do you do that? Because you don't want to run into the curse of dimensionality. Now, who can tell me what is the curse of dimensionality? What is a curse of dimensionality? What is that? I know you guys are smart too. Okay, let me go to Caroline. Caroline, what is a curse of dimensionality?
No, please, I have no idea.
I elect somebody to answer for you. Mention somebody's name.
Okay. Edward Nyame.
Edward. Are you sure Edward is here before you mention his name?
He's facing some network challenges.
So pick another person.
Okay. Augustine Kumado.
Augustine, are you here?
Yes, Doc, please, I'm here, but I can't speak to that now, please.
Why? Why, Augustine?
Doc, please, I don't know. I don't know the meaning of case of dimensionality.
Yeah, you should say that. Why is I can't speak to that? It's like you are busy, so you can't speak to that.
Oh. No, Doc. No, Doc.
Okay, so pick somebody.
Messi Lavi.
Okay, Mercy, go ahead.
So, Doc, from my little knowledge, when you're analyzing data with many or varying variables, it becomes complex. So that's one of the case of dimensionality.
Okay, you said something. You said something. So the case of dimensionality happens when the number of the variables, the independent variables, are more or too close to the number of observations. So you have the sample size, and then you have the independent variables, the features, the regressors. And these regressors are too many. And so when you fit each regressor on the observation, the dimensions of the regressors are too many. And therefore, it makes it very difficult to, it kind of squeezes the sample. And so, because you always want a larger sample, but if the independent factors are more, it makes the sample not sort of larger, simply because the independent factors are more. And now you fall into that case. So the dimensions become many. And so you fall into that case. And we need a way to handle it. So one way to handle it is to reduce the regressors, the independent variables. Reduce them. And one approach to reducing them is principal component analysis and factor analysis. Now let me give you a scenario, another scenario where this thing is very, very important. For example, if you look at the Ministry of Agriculture, they want to determine if a relationship exists between patriotism and consumers' attitude about domestic and foreign goods. So if you wear your made in Ghana goods, then it means you are patriotic. Okay, good. Question is, how do you even measure patriotism? How do you capture attitude? So there are certain things that are very abstract. And because they are abstract, it's very difficult to capture them. And that is where this method comes in, because it will be able to now capture them, give them a certain load, a weight, a factor load that will make them very useful. Another example, the CEO of Ghana Commercial Bank wants to measure the bank's image. How do you measure the image of a bank? Oh, and by the way, you can use a lot of machine learning models for some of these things, especially natural language processing. Okay, I can do that. But we are looking at it from the perspective of abstract concepts. Papaya wants to evaluate the aptitude of salesperson. Again, that is some sort of abstract. So principal component analysis and FA can help you to measure these constructs, patriotism, attitudes, image, aptitudes, all of that. It can help you handle them. So that is why you need them. Another thing is that you have so many financial variables, ratios, like 120 ratios, return on asset, return on equity, expense, net interest margin, all of these, liquidity ratio, leverage, capital adequacy ratio, and all of that. Too many ratios. Probably that's why I didn't do accounting. And now you bring it down. You bring it down. You got to bring it down because the ratios are too many. How do you bring it down? Reduce them to just 3. Well, PCA can help you to get to that level. So let's try to get the essence of what PCA is. What the PCA is doing is to forming a new variable from the original variable. And this new variable becomes a linear combination of the original variables. But each one is weighted. Each one is what? Weighted. In other words, each one is giving, each of the variables, the original variable, is given a weight, is given an importance. Just like in a regression, each coefficient is given a beta coefficient. Each regressor, each independent variable is given a parameter estimate. The parameter estimate will tell you how important that particular variable is in influencing the dependent variable. Okay. Now, PCA will do the same thing. It will reduce the dimensionality of P multi-attribute, as many of them, to just 2. It will reduce them to just 3. It will reduce them to just few dimensions. If it is just 2, then it's bringing them back to the XY graph, a Cartesian plane. But then the dimensionalities are many, multiple, and it brings them down. PCA will check the characteristics of the data. It will try and determine those that are redundant and will condense the information, bring it down to what is known as principal components. Every principal component will have an underlying structure in the data. And PCA will combine them in such a way that you don't lose the information. So if you combine someone like Joel Asari and combine someone like Foster Asari, they're all Asari. Okay? But you can combine the two of them without loss of information. That is what PCA is doing here. You are combining them. In fact, part of the reason why a lot of people in Europe and America are doing well is that they like collaboration. Have you seen that thing? So this one is shooting a movie. I mean, we never thought that somebody like Arnold Schwarzenegger, Commando, will ever team up with Sylvester Stallone, Rambo, and then they will act Expendables 1, Expandables 2, Expandables 3. Why? Because collaboration is important than conflict. You are able to get more audience to go and watch the movie simply because it's these two gigantic individuals being collaborated and together. And so you don't have just a gigantic movie, you kind of have a gargantuan movie. You get a gargantuan movie instead of a gigantic movie. So that is what PCA is doing. It's combining the forces together without loss of information. So let's take an objective here. So the original variables are x1 here. You have x2. You have x3. You have all the way up to xp. P is the maximum number of regressors. And now you decide to combine them. You form something we call principal component and combine the x1, x2. Okay. Maybe not all of them. Remember, you have x1, x2, x3. So maybe you combine x1, x2, x3 to PC1. Then you combine x4, x5, x6 to PC2. You combine x8, x9, x10 to PC3. And then you keep going. Now, the number of the combination, the principal components, will be equal to the total number of the original variables, which means that it's possible that you have no combination. And therefore, the PC1 all the way up to PCK is the same as the X1 up to XP. Okay. Now, what are you combining? You are combining linearly. Take note. It's not diagonally, it's not parabolically, it's not quadratically, it is linear combination. But which ones are you combining? You got to combine those that are uncorrelated with each other. Sorry, you got to combine those that are correlated with each other to create principal components that are uncorrelated with each other. Let me repeat that. This is very important because I have an exam question on it. Okay? So you got to ensure that you are rather taking those variables, the original variables, that have high correlations. High correlation. So Joel Asari and Foster Asari are highly correlated. There's no need for Kwesi Ziga to join them. Because when you look at the Kwesi Nokora and look at the Ziga Nokora, there is no Joel and there is no Asare in anywhere with it. And so there is no correlation between Joel Asare and Kwesi Ziga. But there's a correlation between Joel Asare and Foster Asare. So those two can be what? Combined together. There was something in common. Combined together. Now, Kwesi Ziga, let me see another person here, may probably be combined with Albert Senator. Do you agree with that, Albert?
The name is Senalo.
Ah, that even gets better. Kwesi Ziga can be combined with Albert Senalo.
Exactly.
Yes.
Is that true, Albert?
Yes. Yes.
What is the commonality here?
The commonality, I think, is in Senalo and Ziga. At least they are all coming from Ewe background.
Thank you. Thank you. You got it. You got it. You don't eat rough. You got it. Okay. So that is exactly how it is supposed to be. Now, watch this. You combine Senalo and combine that with Ziga. And then you also combine Joel Asare with Foster Asare. Now, Joel Asare and Foster Asare form a principal component 1. And I'll come and tell you why that's so. Then you have Albert and Kwesi will form principal component 2. Now, the thing is that this principal component 1 guys, they should be orthogonal with those other 2 guys who are principal component 2. They should not be related. So, but among themselves, they should be what? Related. That's why they've been combined. But across themselves, they should not be related to these other principal components. Now, why did I give, and this is the interesting part, why did I give Joel Asare and Foster Asare principal component 1? But I gave Kwesi Ziga and Albert Senalo principal component 2. Why? Why didn't I give this? Of course, I can never in any way give Albert and Kwesi principal component 2. I can't do that. Why do you think so? I need intelligence here. No, I don't need intelligence. I need wisdom. Because intelligence does not connote sagacity. The same way taciturnity does not connote imbecility. So who can tell me? Why is it that Kwesi and Albert can be combined all right and create a principal component, but not principal component 1, but principal component 2? I can't give them 1, but I can give, what's the name? Foster and Joel, I can give them principal component 1. Why? Salasi. Salasi, your hand is up.
Hello, Prof.
Yes, go ahead.
Yes. Hello, Prof.
Yes, sir.
Yes. Please, the reason why Joel Asare and Foster Asare can be given a principal component 1 is that there is a similarity in the name. Asare, Asare. So I believe, or I think they can be given component 1, whilst the Ziga and the Senalo cannot be made principal 1 but 2 because there is no similarity in their name, but there is a background to their ethnicity.
That's it. Oh my goodness. This guy has eaten. That is it. That is it. This is wisdom at its apex of the zenith. Okay? This is sagacity at its highest apogee. And that is the sort of knowledge. You see, knowledge is a very powerful thing, guys. Knowledge is the only asset that creates and multiplies all other assets. There are assets and there are assets, but knowledge combines, multiplies all other assets. And that knowledge the guy just vomited into the Zoom is not a small knowledge. It is knowledge at its highest apogeic level. Okay? He brought that background. He says that, yes, they are connected by background because you have Semalog and then you have Ziga, but they are not connected tightly by the name because Asari and Asari are also connected by background, but they go beyond the background. Okay. So they can now form principal component one. So what then do you think is principal component? Principal component one is the first principal component, okay, that will hold the highest level of information in the data set. Every other principal component will hold less and less importance. Every other one will hold less and less importance. So you will see that over time, as the principal components are increasing, the importance is doing what? You can tell me. As principal components are increasing, what is happening to the importance? What's happening?
I think we'll be decreasing.
It's decreasing. That's it. It's falling. It's falling. It's falling. So if you look at first principal component here, PC1, you will see that PC1 is a linear combination of X1, X2, all the way up to XP. Okay, that is what principal component one. But it is not just a linear combination. It is a weighted linear combination. So it is weighted, and the weights are the B11, B12, B13, all the way up to B1P. Now, the weight, this is very interesting. Right? The weight is telling you the importance that particular variable is given to the principal component. So if I create, so let's go to Asari Joel and then Foster Asari. Now, these were separate. I've combined them into principal component one. But what is the contribution of Joel towards principal component one? And what is the contribution of Foster towards principal component one? That is the importance. That's the weight. That is the coefficient. That is the multiplier. That is the importance that Joel is bringing to that combination. That is important. So sometimes when you go to some tables, international tables, Africans, we don't contribute well at all. Okay, there are some countries, there are some countries in the whole world, they are always contributing negatively to the world. It's war. Every time is war. War is what they are bringing to the table. War song. That is their contribution. And so such ones, their coefficient is going to be very, 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 very bad towards the unification, towards the principal component one. So that is it. The first principal component is calculated in such a way that it creates the highest possible variability in the data set. The first principal component explains a greater percentage of the variability. Write it down. A greater percentage of the variability in the data set. It's examinable. Okay. That first principal component, it creates the greatest, the highest possible variability in the data set. It's the most important. It is the most important. Now, I already told you that there should be uncorrelation. There should be orthogonality between the principal component one and principal component two. This is known as a covariance. So that means that the principal component two is supposed to be perpendicular to principal component one. Now, who can tell me, why do you think we are saying that a principal component one should be perpendicular to principal component two? Why do you think that perpendicular comes into the picture? Why? That a principal component one is supposed to be perpendicular to principal component two. Oh, by the way, I hope you know perpendicular. Remember the good old days when we use mensuration? Is it mensuration? No, it's not mensuration. Secondary school, when you are drawing those drawing thing. What's the name?
Angles.
Sorry?
Geometry. Angles.
Geometry, angles. Hey, people have learned things. So Sometimes we go to school, we learn even unnecessary things. Tan theta, cos theta, pi r squared, the path of a grasshopper. Things sometimes we don't even use in real life. But for this one, you are going to apply it to principal component. So why would you think that principal component 1 is supposed to be perpendicular to principal component 2? What does that give you? What impression does it give you? You can tell me. Let me see. But let me call those people who have never shown their faces. I like it. No, I need you to explain. When you say due to orthogonality, you haven't spoken. Why perpendicular? Why perpendicular? Why should it be perpendicular? Okay, I'll leave it to you. Exams. Think about it. Or sometimes think that I need to make it clear. Now, the next factor to look out for is known as the eigenvector and the eigenvalues. The eigenvector and the eigenvalues. Okay. Now, the eigenvector is the one with the highest eigenvalue in the principal component. Now, eigenvectors will give you the importance. Okay, the importance to compute the orthogonal principal components. Now, the orthogonal principal components are the linear combination of the original. We know that. Okay. And you have an eigenvector. Now, the eigenvector will show you the direction. It will not show you just this thing. It will show you the direction. The eigenvalue is a number which tells you how much variability there is in the data in that direction, in the direction of the eigenvector. Now, sometimes these terminologies of the eigenvector and the eigenvalues can be easily understood from the perspective of standard deviations and variances. Eigenvalues tells you the amount of variability explained by each principal component. You see, when you take each principal component, I told you that each principal component has a certain percentage. Okay? And we gave an example that, the asaris are having a certain percentage more than the error diagrams, okay? The Ziga and that of the Senalo, okay? They're having more. The eigenvalues will tell you that percentage value, okay? The eigenvalues, they are normally constrained to decrease monotonically. In other words, the percentages fall from the first principal component and keeps going down until you get to the last principal component. Now, the eigenvalues are supposed to be bigger than 1. And the first eigenvalue is going to be bigger than the second eigenvalue. When they are 1, it means that that particular principal component accounts for more variance than accounted for by the original variable. So you hope and pray that the principal component that you have is bigger than 1. Now, if any of the principal components you have created is not bigger than 1, what does that mean? It means that it's not that important. It's not accounting for any particular great variability in the entire data set. So what do? Drop it. So this is used as a cutoff point. So I'll create a certain graph, and I'll tell you to determine the elbow effect. You use that to cut off how many principal components you have. Remember, the total number of principal components equals to the total number of variables. So if the variables are 100, it means the principal components are 100. And if they are all 100, what it means is that it's not possible to have it all. Because if you have it all, you must as well go for the original data, because the original data is 100. So what you are doing is that you are squeezing that 100 to 3 or 2. Now, the first one is made up of maybe their 100. So the first one is made up of maybe 60 of the 100 combined together. Or let's say the first one is contributing 60% of the original data set. The second one is contributing maybe 25% of the original data set. The third one is contributing 15% of the original data set. The eigenvalue should be greater than 1. The eigenvalues are plotted on a scree plot, and you see it going down. You see it going down, it shows decreasing, monotonic decreasing, okay, at which the variance is explained by the extra principal component. So let's say calculate an eigenvalue, and the eigenvalue is 4, which means that must be incorporated. That principal component whose eigenvalue is 4 must be added, must be one of the principal components. Okay, you can calculate another eigenvalue. You saw that that one is not 4, but it is 1.2. It's still bigger than 1, and so it will also be what? Incorporated. So you now have principal component number 2. You go and do the third one. And the third one, you have 1.1. That 1.1 is still bigger than 1, so you add it. So now you have principal component 3. You go and calculate the next one. Okay, and that next one is 0.72. That principal component is less than 1, so you cannot include it. So now you have gotten to the limit of how many principal components you should have out of the 100 variables. Now the scree plot will be drawn in such a way that you have the variables and the principal component. So as the variables are falling, as the curve is, the scree plot is going down, you will see that the number of principal components are increasing. So the principal components will start from 1 and increase up to the one that you don't like, its eigenvalue. So sometimes, like I said, this is theory, but as you do the practicals, you understand. So this is a typical example of what I mean. So if you look at it, this thing is the eigenvalue here. Okay, you have the eigenvalues here, and as we see this, the first principal, this is number 1 though, okay, but it started at 1.2. And you will see that at point number 2 here, the principal component, this is point number 2, by the way. This point of principal component 2, you will see that the scree plot is bent. It's bent. So that bending looks like a human being's elbow. So at the point of that bend, or where it bends, that is the point known as the elbow effect. And that is where you should stop counting forward the number of principal components. So the scree plot, you draw it, and then you interpret it. All right, so you can plot the eigenvalues against the corresponding principal component using the scree plot. And then the elbow, that is the point at which the curve bends, will tell you the maximum number of principal components to extract. Very good. Now, the scores are what is known as the principal component. Okay? So you have principal component 1, you have that score of 1. Now, how do you interpret the principal components? We've just done an example anyway. You should know the scale-free correlations instead of the covariance. Now, guys, let me tell you something. Anytime you are doing research, you should know whether or not you use correlation or covariance. Best advice, use correlation instead of covariance. Who can tell me why? Oh, by the way, both of them measure some association. But who can tell me why do you need to use correlation instead of covariance? You know, one of the things that you will encounter when you are watching things in Zoom is that, oh, baby there. Maybe there's sometimes when you might say, oh, better. And that stage, that is when you should get up. I've been there. Get up. Get up. Turn off that video and take a little walk and come and sit down and turn on the video. Because when the video is on, And that your friend and now be tunko kuruma. Ne ya hwe wanim. Yee is a very disgraceful act. But when you are not showing your face, the tendency for you to Famuda, it will increase. And so that is why it's normally advisable to show the face. I'm telling you, I mean, you know what I'm saying is true. So right now, half of those who are not showing their faces, go check what is going on there. I'm telling you, I've seen it many times. So try and take a walk so that you can pay more attention. Okay, so assuming the principal components are extracted from, oh, by the way, the correlation matrix does not depend on the unit of measurement. That's the difference. Correlation does not depend on the unit of measurement. Covariance depends on the unit of measurement. So the units of measurement can be kilograms, dollars, bags, gallons. Correlation doesn't mind what that is. So you can find the correlation between variables without needing them to be in the same, unit of measurement. But covariance will suffer. There. So what are the criteria for extracting how many principal components to select? Number one, ignore the principal component at the point where the next principal components will increase the total variance. So go out till you hit that wall. Number two, some people say that, hey, include every principal component up to 90%. So any principal component, okay, up to the cumulative value of 90%. Cumulative is the same as total. Up to the cumulative value of, I asked a question here too. That must be included. Anybody above that is not necessary. The next one approach is that you can also include principal components whose variance are less than 1. Less than 1. Take note. We said that already. The last thing to do is to create the biplot. Guys, biplot is very important. And every year when I set a question on biplot, people always make mistakes. What is a biplot? The word bi comes from which word? Bi. Who can tell us? Bi comes from which word? Just say it. Bi.
Bi comes from 2.
Bi from 2. So how many principal components do you think are needed to create the biplot?
Two.
Okay, so you need 2 principal components. So the biplot is used to check the connection between the observations and the variables. Now remember, it displays the data set, that has a matrix where the columns represent the variable space, whilst the rows will represent the observation space. So as you go down the row, we are talking about the observations. As you go down the columns, you are talking about this. Now, what a biplot does is that it links the principal component scores and the loadings, we call it factor loadings, with any of the 2 principal components that you see. And then it will display that. So you will see that some of the values you are looking for have gone to group themselves with that principal component. Another kind of values or variables, okay, have gone to group themselves with that principal component. So that is how you want to attack this. You want to read some of these things, information here, to be able to capture what we really mean when we talk about the principal component. Very good. Any questions so far?